Yeah, hello together. Good morning, good lunch, or and good afternoon or good evening. So today we have a presentation from Marina Sousani. She is from Greece, but has a, let's say, international European career. So she started her PhD in Great Britain at the University of Leeds in rock mechanics. And then after her PhD, she went to DEM Solution, where she worked on DEM simulations in different fields for a long time, and with a short intermediate step, let's say, by another DEM software provider. She now works for Aztec. Aztec is a company who works more in the civil engineering, so in construction area, and there it is also very important, especially in the field of recycling, to break larger particles. And so she is working intensively on the simulation of rock or of their secondary particles in yaw crushers, and she will present their simulation results today. So we are looking forward to your presentation, Marina.
Thank you very much, Professor. Thanks for the introduction. I'm going to explain a few things about me and about the company I'm working as well during the presentation. I guess, Tulio, you can verify that everything is okay and you see the presentation, so I can start.
Yeah, it's fine. It looks good. Yeah, fine. Marcelo is also here.
Yeah, I saw that. Yeah. I'm going to turn off my camera just for the period that I'm going to be talking, just because the internet sometimes is not very good, so I don't want to mess it up. And I'm going to turn on the camera again once I'm done. Okay, so as Professor Pade said, my name is Marina Sousani. I am located in Greece nowadays. I'm working from home. And I am the European R&D manager in Aztec. This is a new role of mine. I have been working in Aztec since early this summer. It's a real privilege for me to speak to you today. Thank you very much for inviting me. It's great to be here. And in general, what I am planning to do today is talk you through a couple of projects where we bring new technology to a very old problem, a known problem, explaining the methods we have used and the relevant physics, but most importantly, highlighting the limitations that exist in the current science and what is it that we need, essentially. Okay, so a few words about Aztec. The company was founded in the 1970s. The headquarters are in Chattanooga, USA, and there are a number of facilities around the US and a few of them in other places of the world, including Europe, even though you cannot see the European facilities in this map. Aztec owns a number of market-leading companies that they have become global leaders in the manufacture of equipment. And overall, I would say that the vision of the company is to bring a state-of-the-art technology to traditionally low-tech industries, but also a very important part of our, let's say, vision is to stay closely connected with all of our customers. Now, Aztec Industries is a global equipment manufacturer with a portfolio of brands serving material solutions, the infrastructure, and also mining industries. This means that we manufacture more than 100 products, from rock crushing and screening plants to hot mix asphalt facilities, concrete plants, milling machines, asphalt pavers, and material transfer vehicles. Overall, I would say that the portfolio covers everything from rock to road. Okay, so a little bit of introduction regarding this old problem. So the basic design of jaw crushers it hasn't changed much since, I think, 1850s. The basic components, you can see them in the image. We have a moving jaw, which forms a 4-bar mechanism rotating about an eccentric axis. We have a toggle plate that forms the lower linkage and provides some adjustability. And like many old designs, the durability of this machine is due in large part to its effectiveness. So often, older designs can be kind of difficult to optimize simply because the trial and error and the failures and the usage over the years, they have already done most of the optimization for us. But certainly back then, Mr. Whitney Blake didn't have access to DM, which now we do. And so we can use simulation now to see if we can improve the design to be better performing and more efficiently. Now, to do this, we need to consider a number of things. We need to think how we set up our simulations. What is the effect of the configuration inputs on the kinematics of the job? What is the effect of the particle shape, which is very important? What are the best operating conditions for final product quality and machine efficiency? And finally, how do we actually correlate the results of the simulation back to our objectives, back to reality? So in our projects, the key performance indicators that we mostly looked at were the throughput, the energy input, and the product quality. Now, Aztec produces a number of crushers, and these are some of the main ones. The reason I'm showing this slide to you is because I want to highlight that most of the times the feed material needs to pass through a number of crushers and not just one in order to achieve the size and the shape that we want. This piece of information, I found it very recently, and it's quite interesting and important. I'm going to explain why. You can see the rock sizes that each machine can give with the colored areas. And so if we want to get small sizes, we really need to pass through primary, secondary, and tertiary crushing. Now, I'm going to come back to this slide later during the presentation because I would like to make a point about this. Study, and in many of our applications, we break rocks. So the Tavares model is the most suitable one, or at least is the one that we prefer. It uses empirically derived parameters to determine the impact energy at which a particle will fracture, and it has been excessively validated and improved and is available in several DM codes right now. Now, a few words on how it works, even though most of you probably know. We have the DM particles that they come into the system with a predefined fracture energy, and this energy is determined by experiments. Then these particles, they undergo collisions, and if the energy they receive is bigger than their assigned fracture energy, they break. An algorithm is used in this case to replace the mother particles with their fragments, if we are talking about spheres, or just break up polyhedral faces. Now, if the energy is smaller than the assigned fracture energy, then they get damaged, the particles, by having reduced energy, and they can accumulate their damages until eventually they become weak enough to break. Now, you can find the details in a number of papers, and some of the important ones, I have included them in this slide. But having said that, I think that today we have in our audience the author of the model himself, Professor Tavares. And so if you have specific questions about the model, I guess you have the opportunity to ask directly the professor at the end of this talk. Okay, so I'm going to show you two projects that we focused on optimizing the equipment and obtaining a better understanding on the jaw crusher performance for different conditions, but also we wanted to assess the robustness of a candidate design and the effects of particle shape and operating conditions. For these two projects, we used two commercial codes, EDEM and Rocky, to perform the relevant simulations. Now, the objectives or challenges, I would say, of this first project were to understand the relationship between the configuration inputs and jaw kinematics, to extract the necessary inputs to define the moving jaw kinematics in a DM simulation, to understand what kind of simulation inputs we need to have in order to create repeatable and comparable results, to understand and decide the best resolution of the results that are necessary to capture the phenomenon of interest, and to define the appropriate metrics to determine performance. Finally, one of the objectives was to automate the workflow and data extraction to make our life easier, I guess. Okay, so the first step was to gain an understanding of the relationship between the different geometric inputs and the kinematics of the moving jaw. So we constructed a quasi 2D model that we used to extract the inputs that they were required to define the kinematics, and we ran a DOE. Now, the inputs of the first DOE were mostly the toggle angle, eccentric radius, and frequency. And then we used the outputs of this first DOE, which were sinusoidal translations and rotations, and we used them as inputs into EDEM, the commercial code, and we ran a second DOE using the breakage model and different feed conditions. The measured outputs included the outlet mass flow, torque, force, power, and pressure on the moving jaw. So from the first part of the DOE, to gain an understanding of the effects of the different geometric inputs on the moving jaw kinematics, we plot the horizontal and vertical stroke at the bottom, so the lower stroke, and top, the upper stroke. We can see that as the toggle angle increases, the lower stroke also increases with greater change in horizontal than in vertical stroke. I don't know if you can see my mouse, but this is the horizontal increase and this is the vertical increase. We also observed that increasing the eccentric radius results in an increase in the stroke, effectively offsetting the curve higher. Having said that, for the upper stroke, we see no dependence on toggle angle, with the horizontal and vertical stroke being equal. The eccentric radius demonstrates a similar offset, increasing the stroke with increased eccentric radius. Okay, so we run the DOEs, but what about the outputs? What do we need to measure? What safe frequency is required? DM, you know, that's calculated at very small time steps. But the disk space that we have restricts what we can save. This is a major concern when we are talking about DOEs. So DM provides a rich set of data for analysis. In order to compare different jaw crusher configurations, a consistent method of analysis is necessary. The data output is inherently transient with strong periodic fluctuations, as you can see. Hello? Yes? Sorry, I was listening.
Please go ahead, Marina.
Okay.
Go ahead.
Okay, so what I was saying is that the data output, they are transient and they have strong periodic fluctuations. And this is happening this is happening because of the cycling motion of the moving jaw. In addition, there are some startup effects where there is a delay, for example, from the creation of the first particle to reaching some steady state condition. And since The steady state condition is more representative of a normal or a standard operation. We investigate the time to steady state with the goal of minimizing the overall simulated time. So from the first graph, for example, we can see that the first curves, they look very similar at 10 seconds as they do at 20 seconds. And so we have used this interval, and we decided to stop, for example, the simulation. Then. Also, we used a safe frequency of 0.005 seconds to keep a balance on the disk space and export time. Finally, optimization routines are great with scalar objectives, but DM results are naturally very time dependent and very noisy. So how do we convert transient data in a single scalar metric? These are really important questions that we need to have in mind always while we're setting up our simulations. Now, a big question is about how particles are fed into the job. I'm showing here two examples, a constant single particle stream at the top and then a choke condition at the bottom. What we observed is that trends for outlet mass flow were more or less the same for the constant stream and the choke flow, but they were opposite when we were measuring torque. Now, which one is right? Maybe both are correct, depending on what we want to focus on. Again,
j'ai un problème.
Sorry, Benoit, you want to ask something, or we're listening? We're listening. Okay.
Yeah, please go on. I think there was a mistake. Yeah.
Okay. So I was saying that maybe both results are correct, depending on what we want to focus on. Energy usage and cost savings based on that, detailed final product. It really depends on the needs of the customer. Now, the DOE gave us a lot of data to analyze. I decided not to show here specific graphs and specific very targeted analysis, because the key point is the bigger picture. And the bigger picture is that we combined different inputs and outputs. And as we started comparing them, we began to see relationships. Investigating compound variables allowed us to see clearer trends from the results, which helped us identify optimums, which is what we want really. For example, we see that torque has a strong linear correlation to the close size setting of the jaw, both for horizontal and vertical stroke down here. Specifically, increasing the stroke shows decreasing trend for torque. These were some very interesting results that we used later on in the analysis. Now, one of the things we noticed in the data is that the rotational speed has a significant impact on most outputs, and that normalizing by frequency, we could see trends more clearly. For example, if you observe the top graphs, you will see that the lower frequencies, so the frequency from green to pink, it goes up. So the lower frequencies are the green ones and the highest are the pink ones. So what we see is that the lower frequencies, the green lines, require significantly more energy input for vertical and horizontal strokes, which suggests that the system is under greater load or resistant at lower frequencies. Therefore, it needs more torque. We also observe that the higher frequencies, so the pink lines, exhibit much lower energy demands, therefore lower overall torque values. This suggests that less energy is needed to operate at these frequencies, potentially due to more efficient operation or lower resistance at higher speeds. Also, the results seem to be a bit more consistent at higher frequencies. So we see less variability, and we see that because of the area that they cover. Now, on the bottom graphs, where we are seeing the normalized throughput, we observe that as the horizontal stroke increases, the throughput generally increases for all frequencies, indicating that higher stroke values result in better throughput performance regardless of the frequency. We also see that lower frequencies, so the green lines, they tend to have higher throughput at a given stroke length compared to higher frequencies, which are the pink lines. This suggests that lower frequencies yield better performance in terms of throughput. Finally, the throughput results, as with the torque results, they seem to be more consistent at higher frequencies. So we see there less variability. So summarizing the results from this first project, we used multi-body dynamics and DOE, design of experiments, to define jaw kinematics and its relationship with geometric changes. We used DEM and the Tavares breakage model to explore jaw crusher performance for different feed condition and jaw kinematics. We identified some consistent trends for mass flow and torque and their relationship with horizontal and vertical stroke. And we definitely observed that frequency is the dominant influence on torque and mass flow. Specifically, we concluded that lower frequencies are more energy intensive and higher frequencies are more energy efficient. And also that for maximizing the throughput, a lower frequency setting would be better. Now, of course, questions remain about the best methods. What are the best methods for transient data analysis, and what are the best metrics to correlate performance? Now, moving on to the second project, here we set up a number of simulations with various operating conditions. You can see on the table on the left, we used constant feed rates where we had 3 levels, low, medium, and high, as well as different motor speeds and pendulum motion. And most importantly, we used shapes, starting from a roundish polyhedral shape, the P1, and moving towards a more elongated shape, the P4. Now, efficiency of the equipment and operating conditions is critical for design decisions. Standard metrics is the relationship between energy consumption and throughput. The analysis pointed us to the best, of course, not only the best, but also the worst design areas. And from the best area, we concluded that design 29 is probably the best candidate because it gives us the smallest fragments and a big amount of them with the less energy consumption, which is the criteria. Okay, so some bubble graphs. Here, I know they look busy. I'll try to give you the bigger picture. We observed that increasing throughput doesn't necessarily lead to a uniform product, but also increasing energy leads to less uniformity. We noticed that the round particles, which are the pink ones, the round particles require less energy to break, which makes sense to a point. But this is something that doesn't really agree with the feedback that we get from the crusher operators. I'm going to come back to this during the conclusions. We also observed that the round particles, they produce larger fragments and they are more consistent on final product quality. Finally, the less spherical particles, we observe that they break into smaller fragments, but we have more variation in final product size. Now, to all this, we need to consider that the model is shape agnostic, and so we do not have any information on what type of shapes we get at the end of the process, which is quite important. For this project, we managed to conclude to an optimal, let's say, motor speed to reduce the energy consumption. And also we concluded that the less spherical particles require more energy to break. All this variability in the results, it highlights that there is no significant bad design here. We got positive feedback from operators to the overall operation of the machine, but we got some comments that I'm going to explain in the next slide. And of course, the variability always is an opportunity, gives us opportunities for improvement. Now, summarizing the results from the second project, we observed that the particle shape has a significant effect on the energy requirements, on the product mean size, and the product variation. Specifically, we saw that the more spherical particles require less energy to break. They break into larger fragments, and the product is more uniform. Whereas the elongated particles, they require more energy to break. They break into smaller fragments, and the product has more variation. Now, the reason I have the question marks on the energy side there is because what the operators told us was kind of the opposite. So they told us that the spherical rocks, they require more energy to break. And this is something that the model is not able to capture in our cases. Thinking about this, what the operators told us makes sense because let's say the round rocks or round particles are more compact and they're quite smooth in contrast with the other irregular shapes where we have corners, and these corners are the ones that they're going to break really fast, and this probably creates cracks internally inside the body of the rock. So irregular shapes seem to be easier to break and therefore require less energy than the spherical ones. But it is still very interesting the fact that the model is not giving us this result. So shape is really important, and shape is really important, but shape also is important to know what is the shape that we have after the end of the process. And I'm going to explain why this is important in a couple of slides. Another conclusion that we got from this project was that increasing RPM reduced the energy consumption, and increasing power doesn't improve product quality necessarily. Now, all these are very nice in terms of amazing results that you can get out of a sophisticated model, plus when you're using a very good solver that is coupled with multi-body dynamics to solve for the mechanical interaction as well. And of course, when you use highest quality GPU card for fast results. In terms of accuracy, we are using size distributions that reflect reality and particle properties that are calibrated against real rocks. We are rendering using real-time ray tracing. So this kind of simulation setup is really as good as you can get. But this still is not helpful for design optimization. Now, why do you think this is happening? Well, this is because if I run this simulation once, I will get an answer. But if I repeat the same simulation, I will get a different answer. And this will happen every time. And this is because all rocks are different, and they are different and they break differently. And this is great. This is great if we are talking about the foundation of the model, because it is able to capture the reality. But it is really a massive problem when we want to compare designs to take decisions. Let me explain quickly what's happening. The model has some, let's say, sources of variation that allows it to be so good, but at the same time, these sources of variations, they provide great limitations to design optimization. These sources are the fit size distribution, but also the distribution in fractional energy. Now, if you have enough particles in your system, you will be able to represent this distribution. This is what the graph shows on the right, but in crashing applications, we usually have hundreds of particles. We don't have thousands and thousands. So it is very difficult to capture this distribution if you don't have enough particles in your system. And this is going to affect then the forces, the torques, and the material throughput you're measuring. And to add another difficulty to that, we need to consider the child fragment distributions. So all these, they make the model very good, but introduce a lot of problems when we're looking at comparing purely designs. And of course, we need to be aware that the results are different if we are using CPU or GPU, because some basic functionalities, such as the random number generator, they are different on CPU and GPU. And also, even if we are using only GPU, the results are going to be different from one GPU to another. So all these things are really things that we need to consider when we want to compare designs. So let's see how it looks when comparing designs. If we wanted to compare how a hammer breaks rocks, we might want to test how a single hammer breaks different rocks. Of course, we would expect each rock to break differently, and the Tavares model captures exactly that. But what if we want to compare hammers? Ideally, we will want to use the same rock to test each hammer, so that the only difference is the hammer and not the rock. Obviously, this is completely artificial, and we know that because in reality, rock crushing is an irreversible process. We cannot unbreak a rock and then break it again. But let's say that by tuning somehow the model, we can eliminate these sources of variability that I mentioned in the previous slide, such that we can produce the same rock over and over again, so that the only effect we observe comes from the hammer. But this is very difficult to achieve. It requires not only great knowledge of the model, but sometimes it feels like you are hacking. You're hacking the tool. You need to have a great knowledge of the software tool as well, and even then, full repeatability is impossible to achieve. So if you're using polyhedrons, for example, this is impossible to do at the moment. Okay, so I guess you remember the slide. The key point here is that apart from the various crushers that I mentioned before, that the feed needs to pass through, each crusher produces a different shape. The type of shape we have at the final product is very important, because this leads to good quality pavement due to interlocking and surface friction. When the shape is not the suitable one, it has a significant effect on the life cycle of the pavement, something that nowadays is very trendy with all these regulations about sustainability in industry. So there are some very recent studies that are trying to investigate this, but definitely we need more research around this area. So the shape that we get at the end of the process is really important for this kind of applications and for this industry. So to conclude what we saw today, in industry, we are very much interested in comparing designs. Failing to do so means bad business. So when we use simulations, we need to start thinking the right questions. on what are the important parameters, how do we measure them, what is the right physics we need to use, etc. Most importantly, we need physics that will allow us to focus on geometry optimization purely by creating artificial breakout scenarios if we need to, and removing variation that comes from the material. Finally, shape is critical, not only as an input, but more important as an output, as I explained in the previous slide. So we need physics that is able to capture this final shape and the interlocking phenomena that take place. And I think with this slide, I'm finishing my presentation. Thank you very much for listening, and I guess we can have a chat.
Yeah, thank you very much, Marina, for this very interesting and I think for an industrial presentation, very deep presentation, also from the knowledge and also simulation technology which you used. I think very great. And I would like to open the discussion. So who wants to start? Marcelo, you are unmuted. Yeah, Marcelo?
Yes. Hello, everyone. Since the group is a little bit shy, I'll start with a couple of questions, but I definitely have plenty to discuss with Marina. So I enjoyed the presentation. I think it's amazing the number of simulations you guys did there. And it's really nice to see that some of the results make plenty of sense and some others are really open questions. Of course, I think we have plenty to discuss, and I think we can prepare a discussion offline on this. But I think one point that I'd like to raise is, yes, I do agree that when you are comparing designs, what you want, of course, like a good experimenting person, is to limit the variability. And I think in a crusher like this, the population of particles is pretty small. So it really requires you to run simulations too long and actually even restart simulations to get stable statistics. Just for you to know, we have been doing validation, which is something that you haven't done here, in a laboratory jaw crusher with batches of 20 kilos of material, exactly the same batches. And in the lab, we put the 20 kilo batches in the crusher, and the results are quite variable, and we know that. And when you look at the simulations, they're also quite variable. In the lab, it's not a problem to spend a little bit more material, but in the simulation, it really is quite a painful thing to do many batches. So I fully agree that one way to go is to just assign zero standard deviation to your distributions there, that at least the fracture energy component, which is the biggest one, I'd say, and the one that you could, it's quite artificially, but you can really set into zero. It works. I think the model really will be deterministic on that, not probabilistic anymore. The key thing is that the fragment size distribution, I still believe it has to be probabilistic, because otherwise you don't get a smooth size distribution. Because when you replace a particle with a fragments, you never get the size distribution that we get from breaking many particles, because each particle has a different size distribution. But I think even that can be done for scenarios like this, is to basically get an average size distribution that is not representative, but it is consistent. I think it can be done in EDEM right now very easily. In Rocky, it is a bit trickier, because it really goes into the point that you raise, which is even though in Rocky you have the polyhedra, that fragments look very lifelike, you don't have control of the shapes. And we have seen that sometimes by coincidence it matches reality, sometimes it has nothing to do with reality. So it is something that I already written down. If you remember my 2021 paper, if there's one thing that I said, that we have to really look more into alternatives to Voronoi tessellation. Voronoi tessellation, it is essentially a gaming type of thing that people like to look in their video games, shattering glasses. Looks very natural, but it's not the same like rocks. You want to see shapes being well defined, and there's very little control on the algorithms on the Voronoi tessellation, and we're still trying to work with guys in Rocky to improve that, but it's not yet addressed. So I think it is a very good point you raised, that in this area, shape of the fragments is quite important. In the feed, naturally, there is something wrong going on there that I think it's really worth looking, because of course I think the bulkier particles are supposed to be tougher, and I think it is weird that the irregular shapes turned out to be tougher than but it is the funny thing is that it is maybe related to the jaw interactions with the particles, because in the jaw crusher they preferentially position themselves into some positions there inside the chamber. So it is something that could be a funny effect that you're seeing there. But I enjoyed the presentation. I think it really highlights one application that is really important to severability, but on the other hand, it creates a lot of trouble when improving design, comparing designs. On the other hand, I think fragment size distribution, the shape distributions is something that is not yet properly addressed. And in most problems is not a key one, but I think in jaw crushing and in basically cone crushing, it is important. But I enjoy the presentation. My only question would be when you said you actually use MBD, multi-body dynamics, do you actually mean that there is interaction back from the bed to the toggle, which is I wasn't, and is there a chance that in your simulation you lock the crusher or not quite? That part I didn't understand, because I understand that you program well the motion, but I couldn't see if you actually had restrictions like locking the crusher because there's too much power and you wouldn't move as it would.
No, so even though I was not the one that did that part of the simulation, MBD was used. I don't remember now which tool, but MBD was used, and it was giving to the movement of the. It was giving feedback to the movement of the toggle plate based on the particles. But I need to double check that, because it has been a long time and it wasn't me that did that, so I'm not sure how has been done. But what I wanted to say is that, well, you touched a number of things there. It is true that back then when we did these simulations with Eden, for example, Eden didn't have the possibility of limiting, let's say, the sources of variation. So we had to do a lot of things manually. And one of the things we had to do was exactly what you said, to restrict the standard deviation, to minimize it as much as possible, and to do a number of other things as well. Almost hack the code. But nowadays, the latest version of Eden, it gives the possibility of limiting these variations, so you can get some repeatability. But then the other problem is that in these kind of applications, we really need shape, even in the beginning, because the particles, the spherical particles, the spheres, you can get a good idea of the energy environment, but you cannot capture the flow. You cannot capture the interlocking phenomena. So you probably need polyhedral for that, or clumped spheres, or whatever. You need an irregular shape. And then we have the problem when we have irregular shapes that we don't have any information on what the shape is breaking into. So we just break the shapes into the same shape but smaller. So this is a problem. So I echo everything that you said, and of course the fact that when you don't have enough particles, you need to either run long simulations or many short ones. which is a pain in industry, because if you have many different projects or many different designs you need to check, this is also a problem. At the moment we work with what we have, but yeah, the idea is to show what is it really that we need, what will make our life easier, what will make us sell more, essentially, and highlight these limitations.
Okay, thank you very much, Marina. And I think there are already, I have seen it, Johannes was already at camera on. Yeah, Johannes. Maybe short question, short answer.
Yes, just maybe a comment there on the, I think it was a very interesting presentation, first of all, and it is a very interesting problem with this overlaid variance that we see in the, and just a comment there on the difference between CPU and GPU computing, because in the GPU computing, you cannot decide in the exact order that the parallelization will target each computational operation. So, for instance, if you would stack 10 spheres on top of each other, you would have some numerical error somewhere, but you couldn't say that it would fall exactly the same every time, let's say, as a thought experiment. So there will always, for GPU computing, be some variance between two simulations, but hopefully that variance should be much lower in the global context of the bulk material response than, for instance, the parameters you set in the breakage model distribution or so. So hopefully we can contain those problems between CPU and GPU at least. But I think it's an interesting thing there. I was just wondering, in terms of how you run this simulation, do you work with a computational cluster, or do you work locally on the workstation? How do you work with that, with the DOE?
Usually, that's a good question. Usually we run them. We run, well, it depends. We run them locally as well, but we also connect to clusters. So these specific ones, I think they run locally, but we also do this in clusters. The rest of the team is doing that. Now, for what you said regarding GPUs and so on, I agree, and the problems are less visible when we have systems like milling, for example, where we have thousands and thousands of particles dynamically creating more in the system and so on. So at the end, as a bulk, what we get, the results that we get, we might see variation, but it might not be very suspicious or problematic. But in crashing, everything is magnified because we have less particles.
Thank you.
So thank you very much, Marina. I think Malcolm also has his hand, raised his hand, let's say.
There we go. I think I'm up. Thanks, Marina. I'll ask you really a practical question after those theoretical input. Is you mentioned the operators, what they saw, and a specific one caught my attention, that they said the angular particles versus the spherical. What were they crushing that they could have distinct differences of angular and spherical particles and know the difference? Do you know what those differences came from?
You're muted, Marina.
Okay, sorry. So I don't know, for example, what kind of rock it was. It was, I think, a generic feedback, so considering different types of rocks. But what they told us was that actually the crusher, the same crusher, okay, not different crushers, on the same crusher, when they were getting there, when the feed material was elongated or more irregular shapes, the energy, it was less. The energy required was less than when they were putting spherical ones, which is the opposite from what we get from the model for these applications, for this set of simulations. So I was trying to understand this, and I was discussing with some of these people. It seems that the elongated particles, probably what happens is that they have a preferred, let's say, orientation. So they kind of get the right orientation and they go downwards directly on the close side of the jaw, while the more spherical particles, they kind of accumulate more at the top, so there are more collisions and so on. So considering that, I think, and also the fact that the irregular shapes, you know, they have corners and so on, so they, whenever they hit, they will break, it will be the first that they will go. And probably this will then create weaknesses on the particle, because it will probably create some cracks inside, I guess. While if you have the spherical particles and they kind of accumulate at the top, you might also end up with a more, let's say, compacted system where they are kind of protected from cracking for a period of time. So the jaw needs to work probably more in order to make them move and to break them. So this is the explanation I have at the moment, but this is something very interesting that we need to investigate. Also, what I was thinking is that from the simulations, we are lacking some data, so we cannot derive a final conclusion. I think we need to check hits, we need to measure hits of a spherical particle and of an irregular one, number of hits and the forces that they arise per hit, and see what's going on there. So I think that's the thing to do.
I think the feedback I could give is there's a reason some of it's flaky and some of it's round, and it could be they're quite different rock types. So that's one problem, and the other is they come through a classifier and you get effectively bigger rocks if they're round than if they're flat. So plus the thing you mentioned that they can slip through. So I'll be cautious about jumping too far into trying to draw a conclusion. We've all fallen into this before. So getting back to the rock, and Johannes, for example, who's up, has done a lot of it. Are they actually the same rock? Are they different strengths? Quite important in being able to frame the what the problem really is, or what the difference arises from. That you get observations from operators, but you don't have all the information from the operators. So, but quite interesting. Be cautious what you take from them in terms of jumping, drawing conclusions direct. But no, interesting work. Thank you.
Thank you very much for your comment.
Yeah, thank you. I mean, I have maybe also the last, so we have almost 1 o'clock, at least in Germany. So 1 hour is almost over. So one very short question. When you showed, unfortunately, that, if the throughput was low, the specific energy was low, minimized. Yeah. And if you increase the throughput, you also, increase the specific energy requirement. And do you think, I mean, much nicer would be to have such an optimum curve somewhere, where, by a certain throughput, you have the lowest specific energy. But do you think that, it can be optimized in a way that we can have, let's say, at least similar specific energy input even at higher throughputs, because this is usually more economically? So
can you repeat the last sentence, Professor? I didn't get that. So I
was
understood
saying
your explanation, but the last sentence.
you think that there could be an option, you know, by redesigning it, or I don't know, to, let's say, expand, you know, the area of the minimum specific energy to higher throughputs.
I am not sure. I am not sure.
I mean, is it because with low throughput, it's more single particle stressing, and then with higher throughputs, you come to bed particle stressing?
Yes. I am not sure, to be honest, on that. I need to think about the answer to this. One thing is certain, that it depends very much. So, you know, the criteria of throughput and energy is the main criteria, but it depends very much on what is it that is more important for you, because we have customers, as I'm learning, that the energy requirement is not necessarily a problem. So it depends. It depends what is it really that you want to see. This rule, it's I would say, you know, highest throughput with less energy. It's something that I would say most people look at, but I am not sure at the moment what is the right answer to your question. I need to think about it.
Okay, thank you very much. Okay, then from my point of view, I think we are at the end of our seminar today. Thank you very much, Marina, for the great presentation. And hopefully we have more discussions, you know, with you in the future with here the GCC. And thank you everybody who was joining us. There were almost 40 people from all over the world. So I think also great seminar today. Thank you very much.
Thank you very much all for being here. Thanks a lot.
Thank you.
Yeah, thanks, Marina. Bye, everyone.
Bye.